All right, welcome to the web lecture on correlation. So when we looked at lab number one, we were asking about differences, right? Do men take longer than women to pull out of a parking spot, or do people take longer to pull out of a parking spot when someone's waiting versus not waiting? And we did an independent samples t-test to answer those questions because the independent samples t-test is sort of the statistical tool that we use to talk about differences between two distinct groups. For lab number two, we're going to conduct a paired samples t-test. And again, this is because this is the tool that we use when we're looking at the difference between individual scores from pre to post or time 1 and time 2 anytime we measure the same individual more than once. Now in correlation, we're asking a completely different question. We're no longer interested in differences, right? Not the difference between group 1 and group 2 or the difference between your score at time 1 and time 2, but now we're interested in the relationship between your score on X and your score on Y. Correlation is about the relationship between two variables. The Pearson correlation is the most common, and this measures sort of the degree of linearity. So it measures the degree of a linear relationship. So how closely does the pattern of data fit a straight line pattern? So when we talk about correlation, we can talk about predictor and criterion variables. The predictor is typically independent, the criterion is typically dependent, although with standard correlation research, we're not manipulating any variables, and so these monikers are relatively arbitrary. For example, I might predict that class attendance influences class performance. So in that case, class attendance is the predictor and the criterion is performance. But that's arbitrary, right? As we mentioned before when we talked about experimental research, like it could be the other way around. It could be that students who just happen to come to class more do better, or it could be some third variable. So the point is these terms are somewhat arbitrary. One thing that's useful about correlation is we can use the knowledge of one variable to predict a score on another variable. So for example, if I know that there's a relationship between class attendance and performance, I could look at your number of days attended and I could generate a prediction using the y is equal to m times x plus b formula to generate a prediction for how well I think you might do in the class. Now, correlation itself, the statistic can range between -1 and +1. -1 is a perfect negative correlation. And for this, your data points are going to line on a perfectly straight line. So for example, the time it takes to drive somewhere and speed, how fast you're going, there's generally a negative relationship between the time it takes to drive somewhere and how fast you're going. So as you increase the amount of time, as you increase your miles per hour, the faster you go, the less time it takes to get somewhere. The slower you go, the more time it takes to get somewhere. So with correlation, as one variable increases, the other variable decreases and vice versa for a perfect negative correlation. A perfect positive correlation would be the relationship between the number of hours you work and the number of dollars you get paid, right? We're all real familiar with this. If you get $10 an hour and you work 4 hours, you know with 100% certainty that you're going to earn $40, right? And this makes this a perfect positive relationship, right? So -1 and +1 are perfect relationships. You can think about this kind of like a percentage, right? So the only thing that determines how much you get paid is how many hours you worked, right? Nothing else influences how much you get paid other than the hours that you worked. And that makes this a perfect relationship. All of the variability in your pay is directly related to how many hours you work and nothing else. Okay. When you have a perfect relationship, the data points are going to form a perfectly straight line. Now, as that relationship becomes less perfect, right, as there are more things that influence your x variable and your y variable, those data points are going to spread out around that line, right? And the more they spread out, the closer that correlation gets to 0. And 0 means no relationship, right? So the number of pets you have and your BMI, right? That doesn't really tell me anything about this pattern, right? If I know how many pets you have, that doesn't tell me about your body mass index and vice versa. So these two things are unrelated. And as a correlation gets smaller, as it gets closer to zero, the data points are going to spread out. They're going to look more like a shotgun pattern. They're going to be kind of all over the place. Now, if you think about correlation conceptually, it's the degree to which the two variables vary together and the degree to which they vary separately. So the thing to imagine is, imagine that for height and weight, we can know all of the different things that influence your adult height and weight, right? So there's variation in people's heights, there's variation in people's weights, right? And that variation is due to a variety of factors. And if we could know all of those factors, we could get 100% of the variability in height and weight. And so what we'd want to know is how much of that variability is shared, right? What things influence both your height and weight together, right? And what things influence both your height and weight separately. So you can think about this in terms of a circle, right? So if X is height and Y is weight, then this circle represents all of the things that influence your height, all of the things that influence your weight. Now, some of those things are going to overlap, right? So genetics, for example, your parents' height and weight, right? Those genetics are going to influence both your height and your weight, right? And so that's the overlap, right? That's that covariance, that's that part. But things like how much you had to eat last night, that's going to influence your weight, but that's probably not going to influence your height. And so that's going to be variability that goes over here that's related to just weight alone. So the more the more shared variability we have, the more these two circles are going to overlap. The less variability that's shared we have, the less they're going to overlap. So for example, height and weight in children is very strongly related, right? As children get taller, they also get heavier. There's a really strong correlation. So this is going to look something like this. We're going to have our data points very clustered tightly around this straight line pattern, and there's going to be a lot of covariance, right? If I know how old you are as a child, I can predict how much you're going to weigh with a high degree of certainty because those two things are strongly related. On the other hand, weak correlation is going to look something like this, right? There's going to be no real linear pattern. These two circles are not going to overlap, right? The variability, the things that influence your BMI are completely unrelated to the things that influence the number of pets you have, right? And so this is going to be a very weak or low correlation. So we've talked about this idea that correlation does not imply causation, and so I always put this comic up because I think it's funny. You might get it, you might not, don't worry about it. The thing is, correlation does not equal causation. Remember, we talked about with experimental methods, you must have covariance, you must have correlation in order to have causation, but correlation alone is not enough, right? There's a significant positive relationship between arm length and IQ in children, right? Does IQ cause arm length? No. Does arm length cause IQ? No. Children who are older happen to be smarter. We talked about ice cream sales and drowning. There's a significant positive relationship between the number of kitchen appliances that a woman has and her proclivity to use birth control, right? Does that mean that having an extra toaster or having a Ninja blender is going to cause women to use more birth control? No. The third variable that influences both of those things is socioeconomic status. Women of higher socioeconomic status are more likely to use birth control and are also more likely to have more kitchen appliances. Right? So just because two things are related doesn't necessarily mean that one thing causes another. Now, correlations, we can talk about the direction, so whether it's a positive or a negative correlation, but we can also talk about the strength of that correlation. So Cohen, who's a big statistics nerd, he says that, all else being equal, a correlation of 0.10 is weak, 0.30 is moderate, and 0.50 is strong. Now, it's not just about the size of the effect. So remember we talked about effect sizes and power, right? So the size of the effect here is the size of the correlation. As it gets closer to 1, that effect size gets larger. The correlation gets larger. Correlation is an effect size. But that's not the only thing we think about when we're assessing the statistical validity of a correlation, right? So let's say we find that taking aspirin once a day decreases risk of heart attack among people ages 45 years and older with heart disease, and the correlation is 0.03, right? Is this an important correlation? I would probably argue that it is. It's a weak correlation, right? Objectively, it's a very tiny effect. But because we're talking about decreasing risk of heart attack, right, this might be important, right? It might be meaningful. Versus if there is a 0.3 correlation between the amount of hours you spend playing video games and the quality of your relationship with your significant other, right? That's arguably a relatively less important or less meaningful correlation. So when we think about statistical validity, we're thinking about the size of the effect in relation to the variables that we're working with. We also think about it in terms of the sample size as well. Right, that's what I just said. So generally speaking, the larger the effect size, the more likely we are to get a statistically significant correlation, and really this is true for many statistical analyses. So the larger the effect, the easier it is for that effect to be statistically significant in our study. But also, the larger the sample size, the more likely we are to get a statistically significant result in our study. And so what this means is that as a correlation gets smaller, it is more likely to be significant with a larger sample size. So notice here, with a sample of 25 and a correlation of 0.35, what Cohen would call moderate, that's not a statistically significant correlation. But a correlation of 0.25, which is arguably smaller than 0.35, if you increase that sample size, that is statistically significant, right? So as that sample size gets larger, weaker and weaker correlations are statistically significant. And so this gets into this idea of the difference between statistical significance and practical significance, right? If I have a sample of 5,000 people that's representative of the United States, and I find a tiny, tiny weak correlation, there is a 0.02 correlation between the amount of sleep that you get and your body mass index, right? So there's a relationship, the more sleep you get, the healthier your lifestyle. But the correlation is 0.02, it's really weak. So even though it's statistically significant, right, it may not be practically significant, right? And so this is one thing to keep in mind, this relationship between effect size and power, right? As the sample size gets larger and larger, as your power goes up, weaker and weaker, smaller and smaller effects become statistically significant. So when we're evaluating statistical validity of research that's presented in the media or research that we come across when we're just reading our research papers, we need to think about these things in order to assess sort of that statistical validity. So when we calculate correlation, obviously we're not going to calculate any correlation, but you may in your senior thesis project have to report a correlation. So I'm just going to give you some example here. Let's say there are 30 classes per quarter and the final exam score ranges from 0 to 100%, and I'm interested in knowing if there's a relationship between class attendance and exam scores. The research hypothesis, there's a positive relationship, and when we do our correlation, we state the results in English. We have to talk about both the direction and the nature of the relationship, right? Whether it's significant and what the relationship means. So there is a significant positive relationship between attendance and final exam scores. And when we report that correlation, we're going to report R parentheses is equal to the correlation statistic itself, and then P is less than or P is equal to whatever that significance value is. Okay, so that's the super quick correlation lecture. Make sure that you enter your lab number 2 data, and then check back in for the lab number 2 results video, which should be available very soon.